All right, welcome everybody. Thank you for coming. I hope you're having a great day here of day one of NDC Oslo. I am absolutely crushed that I cannot be there with you, but it is not all bad in the sense that it is 8:20 a.m. here in Phoenix, Arizona, USA, and it is a balmy about 17 degrees Celsius outside. So as soon as this presentation is over, I'm going to be opening up all the windows in the house and enjoying that. So it's not all terrible. I am a solution architect at Carvana, and I tweet at BS Stahl, and one of the things I just tweeted was the link to the slide deck for that, the exact one that you'll be seeing here. In fact, see, we can kind of, hopefully you can see that zooming in. Now, this is a good test of the uh, Zoom capability that doesn't look like it's going to work. So we'll have to keep that in mind. I'll try and make the fonts as big as possible when we're looking at code. So um, you may know me as the guy that keeps a list of his favorite physicists and favorite mathematicians. I see zooming did work. Excellent. So that is probably all you really need to know about me, the fact that I have such a list. But there are other things that are kind of important to know too. I do work for Carvana. We are disrupting the used car space here in the US. We don't have an international presence yet, but for those who are from the US, I don't expect an international presence very soon from Carvana, but it is an amazing place. So check it out if you're in the US. Uh, I also contribute to and shepherd a number of open source projects. None of these are particularly germane to this talk, but there is one that may be coming out soon, I'm hoping, um, that would be very germane to this. I won't be talking about that today, but maybe next summer at NDC Oslo as well, um, hopefully. All right. The other thing I do is I'm one of the founders of Arizona's Give Camp. So Give Camp is an international organization where we put a bunch of software creators together in a room for a weekend with a bunch of great local charities, and we code for those charities for that weekend. And as a former NDC speaker has said, sleep is optional, caffeine is provided. So they are all over the place, although obviously COVID has put a bit of a damper on much of our activities. I encourage you to check out givecamp.org and see if there's one in your area. And if there isn't one, maybe you want to start one. Um, Feel free to ping me for information and or advice. All right. So we're here to talk about reliability patterns today. And so we're going to use this very, very simple example of two things that result in a change to system state. These are two things that we need to have happen. So the example we're going to use is sending an email and writing a state to the database. But these are really proxies for any two state updates within a system. So you can think about this in any context, but these are the two examples we're going to work with today. And our example system might look something like this to start off with. It might be a user connects through a web client to a web service, and the web service inside its web method sends the email and saves to the database. And that might result in some code like this. There's, that's pretty straightforward. I mean, you'll have to kind of trust me that the code does what it says it does, although all of this code is in GitHub and is linked in the slide deck that I tweeted out. So you do have access to all of this code. This particular example does a lot of the right things. It traps for errors in each of these methods. It retries multiple times if it can't, if it doesn't do what it should do. So it does many of the things we would think of. So what does that result in? What we end up with is these possible conditions. So our happy path, if everything succeeds, great. We're in a perfectly good situation and all is well. However, when things don't work perfectly, what are we left with? Well, if our first task fails, that's the send of the email, we're probably still okay. We've done nothing, but we've done nothing. So it's okay because we can just kind of retry later and know what state we're in. We're in a known state. We've failed, but we've failed completely. The hard part, the bad part, is when we get into that last box here, where we've sent the email, but the database update failed. Now we've got a problem. Now we're in a situation where it's going to be hard to remediate. It's going to be hard to do something about it. It's not a good situation to be in. So what can we do about that? Well, a standard example is something that I've done in the past, I know, and I know other people have done as well, is to say, well, why don't we wrap that database call in a transaction and then do the email send in the middle? So something more like this, where the first step is to begin a transaction, do the email send, and then all we have to do at the end is commit that database transaction and we're good. That should be pretty safe, right? Well, let's look at what that actually results in here first of all. We've now kind of split that middle box. So in the previous one, we had a box where we were okay because nothing happened, but we were in a known state, nothing happened. Now we've got two different conditions that cause that. If the database, if the begin transaction fails, nothing is done and we roll back. If the email send fails, that's fine because we'll roll back the database transaction. So we're still good. We haven't made any state changes to the system, but we still have this last box here that's a real problem where if we fail on commit, we're still in a bad situation. Now, the question is, how often does that happen? Do we really fail on commit? And I, at least, and I suspect others as well, didn't fully understand how the service level agreements work with our dependencies like databases. It turns out that if you look at just about any service level agreement, they're not based on number of actions. They're based on time. How long a transaction is open or how long any activity is open tells you how likely it is to fail. So the longer an action is being taken, the more likely there is to be a network failure during that time or a hardware failure or something like that. So this, because the transaction is open for a fairly long time, is actually more likely to fail than the previous one, even though that seems counterintuitive. So where does that leave us? Well, first of all, we should always try to retry. We should always assume that our upstream is going to retry if there's a failure. So if we assume that, we've kind of got two different ways we can treat right now in this context. We've got two different ways we can treat a failure. Like we can either continue if we fail, or we can what I called roll back here in this, which is really throwing an exception at this point. And those are listed along the top here, what these scenarios are. And then along the left side, we've got the different conditions that we could run into, where we could have both tasks succeed, both tasks fail, or combinations thereof. And what we end up with is some states that I just consider not good at all, and those things that we should never use. That's continue on either task failure or continue if A fails but roll back if B fails, although this you could consider a special case of this second one, which is roll back if A fails and continue if B fails. So let's talk to these two that are here in yellow, the second column and the fourth column. So this one, the roll back if A fails and continue if B fails. What that does is it actually works in most scenarios. If, and I've changed my my graphics here a little bit, but if both tests succeed, we're always going to be good. But if A succeeds and B fails, since we're rolling back on A and continuing on B, we're going to end up having done A, but not B. But if B, if A fails, we're going to roll back completely, nothing will have been done, and then we'll retry at the client and we'll be okay. So this scenario is okay if we don't care about action B. So I actually consider this the logging scenario. If we're making a state change to the system and logging it or doing something else that is not critical to the operation, then we're okay. So I consider logging to be one of those examples. And I'd say under these circumstances, under a situation like logging, it's okay to do this. Likewise, there's this fourth column here where the weirdness comes if A succeeds and B fails, and we're rolling back if either task fails. And what that's going to do is, since A succeeded, but B failed, we're going to roll back and we're going to try again. And what happens is A is going to get double tapped here. A is going to get executed twice. So if that's sending an email, we're going to send 2 emails off. This is what I consider to be the idempotent solution. And that is, it's okay to do this if this first task is idempotent, can be done over and over again without causing problems. And we'll talk more about idempotence here in just a few minutes. So what does this mean? Knowing that we have all these different scenarios, and if we're trying to do 2 things, and we have this logging scenario that's kind of okay, and we have this idempotent scenario that's kind of okay, where does that leave us with our applications? And what it comes down to is this. It is not possible to reliably make more than one state change to a system in a single execution context. You can't reliably do it. Now, it's okay to do if the first one is idempotent, or the first change is idempotent, or the second change is made unreliably, like in our logging example. But if we're making 2 important changes to system state, and neither of them is idempotent, we cannot do it reliably. So what does all that mean? Well, let's talk about idempotence first. Idempotence is one good way of helping solve these problems. So let's talk about it. Idempotence is the ability to execute a task some arbitrary number of times and have it be the same as if you executed it once. So the kind of canonical example here is these train controls. That big green start button there. If the train's off, you hit the start button, train starts up, hopefully. You hit that start button again, nothing new happens because the train remains in a started state. So you can hit that button as many times as you want, and the train is going to remain started. So it's the same as if it executed only once. The stop button is the same way. There are a number of operations computationally that we can do that are idempotent operations. The absolute value function is one. And there's actually some useful ones too. So first of all, anything that's not making a change to state is idempotent, right? If you're not making a state change, you can do it as many times as you want and the state is going to remain the same. So you can say read from a database, and that's not, there's no state changes there. So that's an idempotent operation. Another one is a database upsert. As long as you send the key along with all the data that you need to upsert into the database, then what happens? Well, the first time you execute it, if you have no data in there at all, it inserts the row. And then the next time you execute it, since you sent it the key, it will see that that key is already there and it'll just update it. And since it's all the same data, it updates it with the same thing. So database upserts are another example of idempotent operations. These are the things that if we execute them multiple times, it's all right. So that we can use those to help us make our systems more reliable and less prone to failures. But what all this tells us, the these states and these requirements is that we need to try to avoid dual writes, this dual writes anti-pattern. So let's talk about that. Let's figure out what that is, define it, and then figure out ways we can avoid it. So a dual write is an attempt to make more than one reliable change to a system state in a single invocation. Now there's some words in there that probably need to be defined, so let me drill into them a little bit. In this case, what I mean by reliable is can be expected to occur exactly once in that context. And really maybe it should say once or 0 times in that single execution context. You'll either know it fails or know it succeeds, one or the other. And that, of course, is very dependent on the reliability of the execution environment and such. By change, I mean an atomic operation, an atomic modification. So you can change as many tables in a relational database, for example, as you want, as long as it's made in a single transaction. One atomic update. And then the hardest part of this to define is an invocation, a single invocation. What do I mean by that? And maybe the easiest way to demonstrate this is with an example, and that's say, a web method. So I'm going to send a signal, an HTTP call to a web method. What executes between getting that call and returning the response to the external, that's a single invocation. So it's one response to a user signal. And if we try and do 2 things in there, we may have problems if one fails and one doesn't. So we want to avoid making more than one reliable change, or more than one change that needs to be reliable to system state in a single invocation, a single execution context. And the thing about these are really difficult problems to solve when they occur. These are usually results of hardware changes or network failures or something like that. And of course, we're all running on commodity hardware in the cloud, right? And we have all kinds of network hops in between our actions and our users and such. And so what ends up happening is, because they are unpredictable errors, they manifest in very different ways when there's dual writes involved or multiple writes involved. So we could end up with duplicated data or missing actions. It can be incomplete. And the thing about these are, supporting these can be really, really difficult, because you don't have, first of all, we don't know what they look like, because they're always different. So there's no way to say, oh, I know I've seen this error before, because they're all different errors generally. And our tools don't directly support them, because our tools, like if we had a web method that had multiple actions in it and one of them succeeded and one of them failed, we can't just call that web method with the proper data because one of them already succeeded. We only need to do the other one. So our tooling is also much more difficult. So what we end up doing for a lot of these kind of things is creating one-off database scripts to handle these problems, to do updates, things like that. If you find yourself doing a lot of one-off database updates, that may be a smell that you've got this kind of problem. So something we want to avoid. These are your nights and weekends that you're spending troubleshooting and supporting these activities on these applications. So avoid dual writes. Keep it separate. Keep actions separate in order to keep them safe. So what we're going to do now is we're going to spend the rest of this talk talking through some patterns that will help us keep it separate. We're going to talk about 3 very similar isolation patterns that allow us to separate those activities into different execution contexts. Do them individually, do one thing at a time, so that that one thing can either succeed or fail, and then we can react to it downstream. So we're going to look at these 3 isolation patterns: transactional outbox, change data capture, and data streaming. And then we're going to look at the saga pattern and 2 different ways to implement that to bring all of those together. So we have all these individual services that are using these isolation patterns, and then we'll use these coordination patterns to put it all together. And all three of these isolation patterns, transactional outbox, CDC, change data capture, and streaming, all really look something like this for our example. So we still have the user that is making a request, and that request is still stored in some form of a data store. I'm being inspecific about what kind here. But the big difference is then downstream of that is where we're going to grab that and send the email. And all three of these patterns will do basically this. It's just the implementation and when they're best used that changes. So let's talk about the first of these. Let's talk about transactional outbox. And when I think of transactional outbox, I usually think of something like a SQL Server. But many database servers support this kind of. In fact, anything I believe where any database that you can make that supports transactions, where you can make an atomic update that has two different components to it, will work for this. So the goal of transactional outbox is to reliably update a data store and then trigger an additional action. Just like we saw on the last chart, we're going to update the database in this case, and then we're going to trigger an action downstream. So what we do is we make a single write to that database. So our user request comes in, and we make a single atomic write to the database, but we're going to write two things in that transaction. We're going to write the state change that we want to make, and we're going to also separately write a command that's going to be used to execute a secondary process. And that's what's going to be used to send our email. So it might look something like this. This is a sequence diagram. And you can see that in this case, the user is making a request from the request service. That request service updates the SQL database, which then responds that it was successful. And then we have this separate email service kind of looping in here that's polling that SQL server and saying, do I have any new messages? Do I have any new commands in that outbox that need to be handled? And if so, it uses that information to send the email and then has to commit the fact that it did, in fact, send the message, that it's handled that. Otherwise, we'll keep getting emails sent over and over again. Now, when you look at this, you may very well say, isn't that doing two writes? And it kind of is. We haven't solved the two generals problem yet. And if you're not, I'm not going to go into what the two generals problem is in this talk. I do encourage you to do some reading on the subject. It's very interesting. It's a little more computer science-y than we tend to deal with in application development. But it is kind of important to understand that there is still no way to truly confirm, if I send you a confirmation, then did you get that confirmation? Are you going to send me back a confirmation to confirm that you got that confirmation? And then if I get that confirmation, that's ultimately the two generals problem. We still have that, but we're going to have that no matter what we do, almost. So all of these patterns are still going to be susceptible to that. The idea is that we don't need an additional one, and this is as reliable as we can possibly make it. So let's see what that looks like in some code. And all this code is available in the GitHub repository. Let's look at the first demo. This is Outbox. Now, all of the solutions, hopefully, let's see if we can drill in on that. So all of the solutions have both services in them. A request service, which is our ingress, that's where the request comes in. And in this case, it pushes that out to a SQL server. So it just gets that request, pushes it out to the SQL server. First thing to do, get it safe, get it on disk. Then once it's on disk, the email service is polling for that. So all we're going to see in all three of these examples is that the email service, the thing that is reading the results and then sending off the email, is going to be different in how it has to handle it, each one. Those are the biggest differences in these patterns. So we're going to focus on that. So this is our program for our email service, and you can see that what it does is it gets a service and calls process on it with a cancellation token. And what that does is it loops here until it's canceled. Hopefully this is big enough that you can see it well. Let's see if I can zoom just a little more. So it loops until it's canceled, and then calls get unsent messages on the repository. So it's calling that SQL Server and saying, give me any unsent, or give me an unsent message if you have one. And if it does have one, it then sends the email and updates that the message has been sent. Pretty straightforward there, right? So both of these services are very simple. They do one and only one thing, with the exception of the two generals problem. And it keeps it separate. So what does that all mean? What does that do for us? Well, we have some advantages. First of all, it allows us to persist quickly. And that's kind of the goal of all of these patterns, or one of the goals of all of these patterns, is to allow us to immediately get our requests to disk. First thing, customers send you some data, get it on disk, get it safe. We've got that request. And then take some action downstream. The Outbox pattern captures every update. Not every pattern that we're going to talk about today is guaranteed to capture every single update. We'll talk about that more when we talk about change data capture next. And the other advantage of this is it's very familiar tech. Everybody has used relational databases before, I think. Maybe I'm just old and I've always used them, but it, to me at least, is very, very familiar, comfortable technology. However, it can be very hard to both scale and to fan out. So if you think about SQL Server or any relational database, if you're going to scale the number of email services, so the downstream, if you're growing to the point where, you know what, you need more than one email server, it's not likely that you'd need more than one email processor, but you can imagine downstream things that actually require more capabilities. If you're going to need to scale that out, you're going to have to build all of the row locking and things like that into to make sure that only one instance of your service, of your email service, gets that record and processes it. That's all on you. Likewise, if you're going to fan it out, if you want, now I don't only want to send an email message, now I also want to take some other action, send out a message to a service bus or something else, I'm going to have to create a whole new processor, which means I'm probably going to need to either create a new column in that database that gets updated, or more likely create a new table that gets written to, a new Outbox table that gets written to within our transaction, making that transaction even longer. So this is not a good pattern for scale up or for fan out, for allowing additional, extending the capabilities of the application. It's also really using the database kind of as a queue. And I've always kind of felt kind of queasy about that. We have tools for queuing and things like that. And maybe we should use them when what we're really doing is trying to create a queue, a first in, first out data structure. As I mentioned, it adds weight to the persistence, because now instead of just persisting our state change, we're also persisting another thing that goes inside the transaction. That's our outbox. So the longer our transactions, the less reliable, or the more opportunity there is for failure. Although, because they're all in a transaction, it will roll back together. So we know we haven't done anything if it fails. And again, like every pattern we're going to see here, it is still susceptible to errors on the commit phase. So we haven't solved two generals with this one. I'm keeping an eye on the Slido SLIDO room here. So if there's any questions, please feel free to drop them in there, and I'll do my best to answer them. So I don't see anything in there right now. All right, so let's move on to change data capture. So change data capture has a goal of reliably updating a data store and triggering an additional downstream action. Now, if that goal sounds familiar to you, it should, because that's the exact same goal as Outbox pattern had. We're going to update the data store, and then we're going to use that to do something downstream. In this case, however, we're going to do a single atomic write that makes one update to the database, just as we did before. The difference is, instead of us creating a separate Outbox table that we're going to use to persist downstream, we're going to use the database's features to actually do that. So the database is going to do a lot of that work for us. It captures changes to the database and then can event those out to us so that we can use that to process downstream actions. So what does that look like in a sequence? Well, basically the same as before. In this case, I'm going to use Cosmos DB as the example, and that's the example that's in the sample code in GitHub. So we have our request service. The request comes in there. It updates the Cosmos DB. All it has to do is make our state updates, and it confirms that that's done. And then we have our separate email service that is actually notified. Now, the .NET SDK for Cosmos does a great job of handling this and hiding a lot of the implementation details. What really happens behind the scenes is there is some polling going on, but from the application's perspective, we just get notified that a new message is there, and we can handle it. So when we get notified that there's a new message there, we can send the confirmation email, and then it gets confirmed that the message was sent, and we commit. So let's look at the code for the back half of that. Here is our CDC example. And so with this one now, instead of just running a loop, we're actually using a hosted service that runs this Cosmos change monitor. So it's looking for changes. Now, this is the email service. So this is the back half. We've already pushed the change up to Cosmos. And where we see it is in this process message async. So up here, we subscribe to it, our change feed processor. This utilizes the Cosmos change feed in the Cosmos SDK. And what that tells it, what we're doing here is we're giving it a delegate to this method. So when a message comes in here, we're subscribing here, saying call this method when we get a message. And that message comes in this input. So all I have to do is, and it can actually send multiple messages at once. You get to control all of that. So for each of the messages in the input, logging it out, deserializing it, processing it, and executing, and then ending. And processing it, in this case, is just turn it into an email, message subject, message body, and then send the message. And we're done. And with this one, in the change monitor, the fact that we processed it without throwing an exception, the SDK then automatically handles committing it back for us. So it's there, it's just kind of behind the scenes. That can be hidden. So you want to know it's there, but you don't need to deal with it. And you know that if you throw an exception in any of this processing in here, inside this method or below, it's going to roll it back and it's going to try and send it to you again. The SDK will do that for you. So you don't have to worry about any of those implementation details. So I consider this a much better implementation than Outbox. Although I don't want to make it sound like I'm not encouraging you to use Outbox. Outbox is really useful, especially if you already have a relational database that you're making updates to, and you just want to extend that capability. Outbox is a really good way of doing it. If you're starting from ground zero with Greenfield, which we would all love to do someday, I'm sure, then both CDC and the next pattern that we look at, streaming, are going to be really good choices. All right. Oh, make code bigger on this one. Sorry, I didn't do that. Hopefully you could all see what you need. And also, like I said, it's all there on GitHub. What happens when we run more than one instance of email service? Good question. So in this scenario, and we'll talk through this on the next slide a little bit, but in this scenario, the database will do a lot of the work for us in balancing that load. So we can spin up multiple versions of this, and as long as we've configured it properly, there's a concept of a what do they call those? A consumer group. If you have multiple applications in the same consumer group, only a message will be sent to one processor in that consumer group, and only one. And the server and the SDK handle that for you, manage all that. It's beautiful. Likewise, you can also fan out easily. So if you have different consumer groups, and you run multiple instances of this, or of consumer groups, you can actually fan it out and actually have different services taking different actions and know that each consumer group will get the message once. Really, really useful and valuable. I hope that answered the question there. So, Cosmos change data capture. Again, we get to persist quickly, and it's, as we just discussed, easy to scale and easy to fan out because the database and the SDK together manage a lot of that for you. The biggest disadvantage here is that, at least with the current implementation of Cosmos DB, change data capture, you're not guaranteed to capture every update. If you make a state change and then update that state change again very quickly, you may see only the latest state. So it looks at the current, when it's seeing the changes and saying, oh, what changes do I have? It's only going to give you the latest state change in the current instance of Cosmos change data capture. Other implementations may be different. And Cosmos is actually exploring the Cosmos team is working on, I think it's in preview right now, something where it will actually give you every message if you choose to do so. But right now, that's one of the biggest things that you need to understand is that it's not guaranteed to capture every update. So be aware of your implementation and how it works. Now, if you're just writing messages, so if you're basically event streaming here, where you just throw every message into it and you're never updating a message, then you don't have to worry about that because you're just creating new messages every time. And of course, we are still susceptible to errors on that back commit of the log, which it handles all for us. It's all behind the scenes, but it still can fail after it's executed the process. It is possible. However, unlikely. All right, the last of our isolation patterns, data streaming. Goal, reliably persist a message and then trigger a different additional action. So very, very similar. In this case, though, we're not talking about necessarily a persistent state store. We want to get a message out there, and then we want different things to happen downstream. And we make a single atomic write that puts it into that stream. And it's that stream that's used to trigger all actions. So what does that look like in this case? Well, in this case, I just have it pushing into a streaming service here. But, the more I think about this, the more this is a little bit disingenuous because this is not my state update. This is not necessarily, like if I'm pushing this into, say, Kafka or Redis or RabbitMQ, this is not my state update. So what I really should have is two different services sitting down here, looping and reading these messages. One to update my database, whatever that data store is, and then a separate one to send the email. So that really would have been a better way for me to draw this. But it's still a very, very similar process in the sense that we're pushing a message out to something, and that thing is then going to be used to consume the messages and take the downstream actions. So if there's examples of this in the GitHub code for both Kafka and Redis, using Redis streaming or Kafka's streaming SDK. This one is Kafka. And so you can see, just let me make it bigger. So just like in the CDC option, we're actually using a hosted service. So that's sitting in the background and running all the time for this Kafka change monitor now. The Kafka change monitor also subscribes. In this case, it subscribes to what's called a topic. So messages get put into a topic and they can fan out from there. So it subscribes to that. And when it gets a message, it calls this process message async. So very similar pattern, and then handles it, in this case, just by sending the email out. Like I said, I probably should have maybe a persistence service. That's a third one here for this example, that also writes it out to a database to make these use cases exactly equivalent, where both of them are updating a data store and sending an email. I hope that all makes sense. And again, the code is in GitHub, so feel free to pull it down and play with it. All right, so data streaming. Again, we can persist it quickly, very easy to scale and fan out. All of our streaming systems are designed for that. The one that might not be easy to fan out would be if we're just using a plain old queue. Like, for example, Azure queues or IBM WebSphere queues or something like that. If we're just using a queue, that's not really good for fan out, but it's great for scale. But if we're using a topic where it handles the fan out for you, it works great for both of them. So Kafka and Redis both are really, really good for both scale and fan out. And these will capture every update. So you're going to be able to get all of your updates with both of these. You know every message will be seen. The biggest disadvantage here is that the reliability is really subject to the persistence of the implementation. What I mean by that is, just to contrast Kafka and Redis. Kafka does a great job, immediately persists to the log. First thing it does is get it to disk as quickly as it can. Redis is very dependent on how you configure it. By default, Redis doesn't really go to disk at all, and it's just kind of an in-memory store. So it's wicked fast. But if there happens to be a hardware failure at the wrong time, Redis is going to be more susceptible to that than something like Kafka. And of course, we are still susceptible to commit errors. All right. So as you've seen, these patterns are super similar. You persist first, then act on it. You do one and only one thing. The only thing you're doing in each of those things is reacting to the signal and then doing the specific work that service is designed to do. It's easy in CDC and streaming to fan out, as well as scale. Outbox and streaming both guarantee that all changes will be sent. CDC not as much, so you have to be careful there. But all are susceptible to that commit error problem. Now, is there anything we can do to avoid those commit errors? This is not going to be a satisfactory answer yet, because like I said, we have not solved the two generals problem. We get very close to 4 nines with these patterns, assuming our dependencies are supporting 4 nines. So we can never get better reliability than our downstream dependencies or our network or our hardware, etc. But if we make proper use of idempotence, if we use it wherever we reasonably can, it may be possible to come very, very close to exactly once delivery. Now, Kafka has a specific mechanism that I'll defer you to their documentation where they have a really good write-up on exactly once delivery, what it means, why they feel like the two generals problem is not an entirely germane to that circumstance, and how they go about doing it. But what it really comes down to is still same as what we've described: do one and only one thing, do it idempotently, and then do something else downstream. But there's a lot more complexity there, so we're not really going to drill into that in any more detail today. Know that it exists. At the end of this, if you're not familiar with the concept of exactly once delivery versus something like at least once or at most once, there is an appendix at the end of this slide deck that describes what each one of them means. All right. So we have all these isolation patterns. How do we put them together? And there's two ways of really putting sagas together. Sagas are that coordination of all of those different services. We can do it through an orchestration, or we can do it through a choreography. Orchestration has a single controller, a state machine generally, that is responsible for managing everything and being a single point of failure too. A choreography is where all of the services are really independent. They consume messages, whatever they happen to need, transform them appropriately, do whatever their work is, publish new messages out, independent of each other and not necessarily having to know what happens downstream. So let's look at each of those examples and see what their benefits are. So this is a saga. It's kind of a workflow. You could think about this orchestration service as a workflow, as a state machine. But ultimately what they're doing is it's still all, the user submits a request. That request is persisted as quickly as possible. The orchestration service then has to know, I am at this point in the process and I'm going to publish these messages and look for failures and look for responses and those kinds of things from the other services. Now, I kind of showed them all as different topics here, different buses, but it could be one bus as well. I don't tend to do that, but it's something that can be done if need be. But what this is doing is, at least these first two steps are the same as what we've done before. The orchestration service is going to notify we need to update the database. It's going to send out the email. And then it's also got notifications going to billing and the request action service. So if this service, what it's allowing the users to do is request us to do something. Hey, I need you guys to go and do this thing. We can send them the confirmation email, write it out, send some information to, charge them for it as appropriate, and then send it off to whomever is actually doing the work. Probably Fiverr, right? Something like that. And then if this comes back and says, sorry, we can't do that for some reason, the orchestration service then is responsible for saying, we couldn't service your request. Let's send a compensating request back to the billing service to say, give you your money back. So that's the kind of orchestration we're talking about here. However, choreography, I've labeled as my ideal architecture. This is where I prefer to go, because we've come a long way in the last 10 years. And what I see this as this is what I refer to as the microservices pattern. This is what I see as a good implementation of microservices. You have simple services where all they're doing is one and only one thing, one change to state of the system. They're independent. They read from some data source, transform, manage, do their one thing, and publish some message. And they do so kind of independent of what everything else needs. So I know I need to react to this stimulus. I need to react to some particular message. The upstream may not know that I'm responding to it. I do my work, I publish a message out. I don't have to know what downstreams are using that. All I know is I publish my canonical example, my canonical structure that says, here's my message. Here's the thing I've done, or here's what you need to know about, or, generally what someone downstream might need to know about this thing. And then I don't worry about it. This, I think, is an ideal pattern. There is nothing more powerful that I've experienced than needing to augment a system, needing to add a feature to a system, and already having something, a trigger, an event in the system that I can subscribe to that is exactly what I need to then go off and build that additional feature. That's how we make systems that are extensible, because whatever is doing its work is publishing these messages out, and I can find the appropriate trigger that I need to then do whatever it is I need to do inside the system, the additional work I need to do inside the system. But that comes with a caveat. That additional thing should never be just kind of added on. There is always this tendency, this, I don't know, it's like, if you think about, I need to add a feature here. Well, I've already got this thing that's doing something that's going to trigger it. Why don't I just plug that right inside that existing context? And you're going to get pressure from your analysts, your product people to say, well, just plug it in there. But this is your nights and weekends that they're telling you to sacrifice to support that thing. Because if you add on inside an execution context, you are creating a dual write, and you're creating a situation where there are going to be difficult problems to solve at some point. It may not happen often. It may not happen for a while. But at some point, it's going to happen. And then you're going to have to spend the effort to figure out, A, what happened, and then how do I fix it? So never add on. Never add on. All right. So let's sum up here. We're just about out of time. So it is impossible to reliably take two actions inside a single execution context. I know I haven't fully proven that to you yet. In an hour, it's kind of difficult to prove. Know that I absolutely believe that with as much scientific certainty as I can give you. And that is, I know that there is no such thing as certainty, but I'm confident. So we can't do it. So avoid making multiple state changes to systems in a single context. Break them up. The best practice is always persist first. Get a message, persist it, then take other actions as necessary, ideally in a separate execution context. We can use Outbox, CDC, change data capture, or streaming to help isolate the different features of our applications, the different things that need to change the state of the system. We prefer, it's better to use CDC or streaming for best fan out and scalability, but Outbox is a perfectly good pattern, especially if you already have SQL Server or some equivalent in the mix where you're already populating state. And then consider how you're going to do your sagas to either orchestrate or choreograph these complex interactions reliably. We have some really, we've come a long way in terms of our tools to monitor our sagas. That was always the biggest concern at the beginning of the microservices era, was how do we manage? We have all of these different services out here. Sure, they're simple and easy to deal with and easy to deploy and easy to work on independently. So I can have I can scale my team. I can deploy them out frequently. All of these great benefits we get from these small microservices. But how do we follow a single request through the system? And we know there are certain things that we'll have to do there. We're going to have to put correlation IDs on every request to be able to follow them through. But then with shared logging tools and tools like App Insights or App Dynamics or whatever it is you're you're using, we can actually get even visualizations of the interactions of our systems and see where there are problems and see what's causing difficulties. And using the correlation ID, we can go into our shared logs and actually see across all of our different services, here is all of the logging for that correlation ID. So we can get a full picture of the logs of all of our services, and we can see a picture of the interactions of all of our services and how they work together and what's causing problems with these tools. So I think we've solved all of the problems, all of the big problems anyways. And the problem that we still need to solve is avoiding these dual writes so we can avoid spending our nights and weekends figuring out these complicated problems. So avoid the urge, resist, don't add on, and keep everything separate. One change per execution context. All right. Here's some resources. I do work for Carvana. As I said, the code samples are linked here. Article on idempotence, articles on each of the 3 isolation patterns, some specifics on ways to do streaming, as well as stuff on the Saga pattern. And this is the actual article that got me started going down the path of why our service level agreements don't actually, why it is that our transactions don't make things more reliable, they actually make them less reliable. So I encourage you to read that. It's a little off the bottom of the screen here, but there's also an article down at the bottom on the plant UML tools, because there's diagrams in each of those code that use plant UML to show you those sequence diagrams that I showed. So that's there as well. And all of that can be garnered either by going to my Twitter account at bsstahl and clicking on this link, or by shooting this and pulling down that slide deck and being able to just click directly on all of those links. I don't see any additional questions on here, but it looks like we have 3 more minutes, so I will happily hang out and answer any questions that you might have. And other than that, I thank you for attending and hope you have a great conference.